right, so let's recall that if somebody gives you a group and you find a pair of subgroups, one of them n being normal and the other one h just being some subgroup, and suppose they satisfy the property that their product altogether is the whole group, they don't intersect except in the identity, then we know that that group must be isomorphic to a semidirect product of n with h for some phi, where phi is some group homomorphism from h to the automorphisms of n. So, there you are, you're looking at, groups of order, I don't know, whatever order, like 21 or something like that, and you look at your CLO subgroups, so there you are, order of G is 21, and you find you have some CLO subgroup of order 3, some CLO subgroup of order 7, and you look at your congruences and you notice that this thing is normal in the group, this thing maybe isn't, and then that you have to then say, well, what could the group possibly be? And you know that these two groups, because this one is normal, you can multiply them together and you get a group. Everything, and this group, products of this form a group, and of course the order of that group is divisible by both 3 and 7, and so therefore you have to get the whole group. Of course these things can't intersect because there are groups of relatively prime degree. And so, poof, you know that the group in question is a semidirect product. It's a semidirect product of P7 with P3 with respect to some phi. So all you need to know then is, what is this mysterious phi? Of course, you also need to know, if I grab a bunch of different phis, am I describing different groups or the same group? How do you figure that out? So in order to start to think about this, we're going to need to think a little bit about what do the automorphism groups of groups look like. So it's useful to actually see how to think about these aught-ins. And then if we have different homomorphisms, how do we know if they actually maybe give the same group when you do the semidirect product? Of course, before we can talk about distinguishing these semidirect products, we should take a moment to think about how we would write them in the first place. One of the basic ingredients we need is to understand the automorphism group of a given group N. Automorphisms of groups can be a bit tricky in general, so let's start with a nice warm-up case, the automorphisms of the cyclic group Z mod NZ. So let me start by just saying the answer. The automorphisms are going to end up being the same as, for example, considering Z mod NZ as a ring and looking at the invertible elements under multiplication. This also has the name U sub n for units sub n, and it also can be described as the set of equivalence classes of integers I, such that I in n is 1. I is relatively prime to n. All right, let's just quickly review how that works, because it'll be useful to have a nice concrete viewpoint of this. So if alpha is such an automorphism, then alpha is determined by where it takes 1. So 1 goes to alpha of 1, which I don't know is the class of some a, where a is an integer, and the class of a is its equivalence class mod n. I'll write that in a bar, let's say. And of course, this map has to have an inverse map as well. If it's an automorphism, let's say beta, beta is also determined by where it takes 1. So let's just say beta of 1 is some element the class of b. And so what I would like to say is that we can find such a b exactly when a is relatively prime to n, and that'll correspond to it being invertible in the units. Well, okay, so how does that work? Well, to say that this is an inverse is really to say that beta alpha of 1 is 1, right? I mean, I want to know that beta alpha is the identity map, and the identity map is determined by what it does to a generator, and should send the generator to itself, and that's enough to say it's the identity map. But then I can look at this expression here and interpret beta of alpha of 1 as beta of alpha of 1 times 1. And, so this is just in the, thinking of this as, taking 1 plus 1 plus 1 plus 1, a of 1 times. Now, so here, a of 1 then is going to pull out of the beta. So really what I'm looking at is like, you have some group homomorphism and some group element to some power. So here, phi is like our beta, g is like our 1, and m is the alpha of 1. I'm just using kind of an additive notation instead of a multiplicative notation. And what we know is that in a group, this is phi of g to the m, but written additively, that looks like this is alpha of 1, beta of 1. And I want to know that this is 1, really the class of 1, we should say, I guess, right? Okay, classes of 1. All right. Well, in other words, what we've said is that if alpha of 1 has an inverse, then if I think of it as an element in the ring Z mod NZ, it had better have a multiplicative inverse given by beta of 1. And conversely, if it does, then defining beta in this way will give me an inverse map. Okay, so we can see that the automorphisms correspond to the units in here. And if I unfold this a little bit more, so you can see that what this is saying over here is that if I have an inverse, then I had better, this beta is defined by some b bar or some b, I had better, so the alpha has an inverse is the same as saying that there exists a b such that AB is congruent to 1 mod n. And, well, what does it mean to be congruent to 1 mod n? It means that, that there exists not just a b, but I guess a c, such that AB minus NC is equal to 1. But of course, those b and c existing is the same as knowing that a and n are relatively prime, right? So we see then that that we can make an identification of the automorphism groups with the, I guess I called it A over here, the classes of A such that A is relatively prime to n, and we get this nice identification of the automorphism group. So that is, concretely speaking, we're taking 1 to A bar, and therefore taking I to IA bar. We're just kind of multiplying everything by IA bar, where the thing that we're multiplying is an invertible element modulo n. And those are the automorphisms of a cyclic group. So even for the automorphisms of the cyclic group, the unit group, there's already a little bit to say. Let's look at a few examples. Let's say, for example, Z mod NZ units. I'll just enumerate them. Like there's like the class of 1, the class of 2, class of 4, 5. Just listing the numbers relatively prime to 9, which are the ones that are not a multiple of 3. That's all of them. And okay, what's the structure of this group? Well, it's a group of 6 elements. It's an abelian group because multiplication is abelian. And well, there's only one such group. It's the cyclic group order 6. Okay. Let's take a look at Z mod 8Z. Z mod 8Z, class of 1, class of 3, these are just the odd numbers, class of 5, class of 7, that's it. This is a group with 4 elements. It's an abelian group. And you can see, just by inspection, that everything is order 2, right? 1 squared is 1, 3 squared is 9, which is 1 mod 8, 5 squared is 25, which is 1 mod 8, 7 squared is 49, which is 1 mod 8. And so, actually everything is order 2, so this is just z mod 2z cross z mod 2z. It's by the process of elimination. On the other hand, if you look at a prime, z mod pz star, it turns out this is always cyclic. Of course, order p minus 1. The most reasonable proofs I know of this, already use a little bit of field theory, looking at how to factor cyclotomic polynomials over the field z mod pz, or this is a field with p elements. And so we'll have to even postpone that explanation of cyclicity there. But you can see these have these groups can have various structures. The various structures as abelian groups. I guess one nice thing that does help simplify a little bit is the following fact, which is basically the Chinese remainder theorem. So let's just say, well, first off, an abstract fact about rings. So if you have a ring, which is a product of 2 rings, then the units in the ring are the product of the units. Okay, so this is a pretty straightforward thing to see. If multiplication is done component-wise, the identity element is kind of identity cross identity, if you will. And so if something is invertible, then you have to find the inverse in both factors, and that's how it works. All right. So, okay, that's something. But okay, so in particular, if I have 2 integers which are relatively prime, then if I look at z mod n mz, the Chinese remainder theorem tells us that this is isomorphic to z mod nz cross z mod mz. And that tells me a similar story about these units. Remember, we also had this notation un, a little convenient to write it like this. Un is isomorphic to un cross um, at least if n and m are relatively prime. And so, you can get, without doing the brutal computation, you can look at the units mod 21, for example, and see that this is the units mod 3 cross the units mod 7. Each one of these is a prime, and so these are both cyclic. And so this is a cyclic group of order 2 cross a cyclic group of order 6. Okay, and so that's the kind of thing that one can show with that. All right, and so that's a bit on cyclic groups. So let's look at some groups which aren't cyclic. All right, let's consider as our next case the case of what's called an elementary abelian P group of rank n. So this is where I have a bunch of copies of z mod pz in copies. So by this I just mean you have z mod pz cross z mod pz cross dot 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 z mod pz all together n times. Now this is an interesting nice case because this is not only a group, but it also has the extra structure of a vector space. This is actually a z mod pz vector space. So that is to say, if I have some element inside this group, I'll call it suggestively V, some element inside this group, of course it makes sense to multiply elements in the group by integers. That's really just taking powers in the group, because I'm writing things additively. So we can, define A V, of course, well, this is already defined in the group, where A is an integer. But you can see this only depends on the class of A mod P. Because if you were to multiply by P, everything has order P, that kills everything. And so, you know, A plus P, for example, V, is the same as AV, because the PV is 0. So it makes sense to multiply things in this group by classes in Z mod PZ. And in this way, it's easy to see that, you know, thinking of this as a field, this happens to be the field with P elements, that this elementary abelian group is actually also, for free, a vector space. Moreover, if you have an automorphism, or even just a homomorphism, from G to itself, then because every homomorphism has the property that, you know, if you multiply by an integer, then that integer pulls out, right? This is the, if I write this multiplicatively, it would be phi of v to the a is phi of v to the a, but I'm writing things additively. Well, that also means that because everything only depends on P, that you can write it like that. And that means that every group homomorphism actually is a map of vector spaces, a linear transformation of vector spaces. So for that reason, we get a nice description of the automorphisms. So automorphisms, thought of as a group of G, are the same as automorphisms thought of as an FP vector space of G. Well, as an FP vector space, this is a vector space of dimension n, and the automorphisms of such a vector space are given by n matrices with entries in the field. And so in this case, we at least get a translation of our description of the automorphism group. All right, to get a feeling for where we are so far, let's consider looking at groups of order 50. So if you have a group of order 50, then we know that you can consider the CELO subgroups of the 5 CELO subgroups and the 2 CELO subgroups, subgroups of order 25 and 2, respectively. And we know that the number of 5 CELO subgroups has to be congruent to 1 modulo 5, and it has to divide 2, the index of such a group. The number of 2 CELO subgroups is congruent to 1 mod 2, and in 2 has to divide 25. Okay. A lot of possibilities for in 2, well, I don't know, a couple. It could be 1, 5, or 25, I suppose, right? Okay, but in any case, what we have is that the CELO subgroup P5 is going to be normal in the group, the normal subgroup of order 25. And so the other group may or may not be normal. Now, what is the structure of P5? P5 is a group of order 25, and all groups of order P squared are abelian. So P5 is going to end up being either Z mod 5Z cross Z mod 5Z, or Z mod 25Z. Okay, we'll go into more detail about the classification of abelian groups a little bit later, but for right now, I'll just quote this as the answer. And so we know that G is going to be, for the usual reasons, a semidirect product of P5 and P2. That's just because this group is normal, this group is a subgroup, and if you multiply them together, therefore you get a group. And if you look at the intersection of these two things, it's trivial, and you know that the product P5 times P2, and the product, everything in the group can be the intersection of this has to be trivial because it has to be both a subgroup of a group of order of 5 power order and 2 power order. That can't happen except just the identity. These don't intersect. They generate everything just by the orders have to generate everything, and therefore you have a semidirect product. Okay, so the only question to describe this semidirect product is what's the phi. So phi then is a map from P2 to the automorphisms of P5. And depending on what the structure of P5 is, we can get a couple of different possibilities. So it might be Z mod 25, or it might be Z5 cross Z5. Okay, well, if it's Z mod 25Z, we can look at the units mod 25. So we got class of 1, 2, 3, 4, not 5, 6, 7. Oh gosh, I don't feel like doing this. Okay, well, we can do that. We can look at the group structure. We can look at potential elements of order 2 in that group. Well, Z mod 25, when you look at the units, it's a group of order 24. It's not going to be a cyclic group, but so it's going to have a few different elements of order 2 in it that might be possible targets, and those will give you various semidirect products. Let's look at the other case, though. If I look at automorphisms of Z mod 5Z cross Z mod 5Z, then this is GL2 of Z mod 5Z. And so the target of such a map P2 is going to be some matrix in a field with 5 elements whose square is the identity, a matrix of order 2, an invertible matrix of order 2. So how are we going to make sense of that now? I mean, this is a little bit complicated because there's maybe a whole bunch of matrices of that form. Well, one thing that would be nice is if we could, play with changing the basis so that this matrix had a particularly nice form. Like, that a matrix of order 2 in this way is going to have eigenvalues either plus or minus 1. And by using Jordan canonical form, which is something we'll go into eventually, such a matrix will be, so a matrix T inside of here, such that T squared is the identity, has the form, after a change of basis, well, it has to have eigenvalues plus or minus 1. They could both be 1, it could just be the identity, or they could both be 1 with a 1 on the above. This is the kind of basic Jordan block. They could both be minus 1 with nothing up there, both minus 1 with a 1 up there, or you can have distinct eigenvalues of 1 and minus 1. And up to conjugation, these are the distinct possibilities for T. And at least that cuts down the number of possible matrices I might look at. If I could reduce to only looking at these 5 groups, there's a whole lot more elements inside of here that have order 2. So I'm giving this discussion for a couple of reasons. On the one hand, it's interesting to see that when we're trying to classify these semidirect products, we have to bring to bear a number of tools from the outside. We have to bring in a bit of linear algebra in this, to understand the group of units in, that's also an interesting, non-trivial thing. But before kind of going too far into detail about these other topics like Jordan forms of matrices and such, let's see what kind of tools we have for saying when 2 expressions of semidirect products are actually the same. Like, if I grab 2 different matrices in here that have order 2, how do I know that the groups that I get when I do the semidirect products are the same or aren't? What are the tools that I have to identify these different semidirect products? So let's take a look at that. All right, so let's let's consider the following question. Let's suppose you are given a couple of groups, H and N, and a phi from H to the automorphisms of N. So when you have that, you can of course form the semidirect product in semidirect over phi with H. And the question we'd like to ask is, how do we find or enumerate or list other psi's, also going from H to N, such that you get the same semidirect product? Or an isomorphism between these semidirect products. Now, in some sense, this is a really kind of ugly question because there's kind of a lot of different ways that you could find such isomorphisms, and it's a complicated question. On the other hand, there are at least some straightforward ways to produce a bunch of different psi's given a phi. And if you're lucky, maybe this kind of answers enough of the question to let you relax and get on with your life. So what are the tools that we have given a phi to construct such psi's? Well, one thing that you can do is if you have such a phi and you grab an arbitrary alpha, which is an automorphism of H, you can produce a new phi, or what we were calling psi, in the following way. Instead of just going to aught n via C, you first go from H to itself via the automorphism, then you go over. You precompose with some alpha. And it turns out that if you do that, so this new map I could write as you do psi after, this should be a phi, excuse me, phi. So this is phi after alpha. And if you do that, then the semidirect product that you get with that new automorphism here, the new map from H to the automorphisms is the same as the original one. And it's just very concrete to write it down. If you look at the map that takes a pair NH to the pair n comma alpha H, with the obvious inverse that you can apply alpha inverse to the right, then you actually just go between these two group structures. Just to play with it a little bit, if you look at NH, n prime, H prime, I can, on the one hand, multiply this in here on the phi alpha side, where I would move the n prime past the H by doing I do the phi alpha of H and apply that to n prime. Well, that's a confusing notation. What I should say is first I plug H into alpha, and then I do phi of that. Well, that's phi of alpha of H. Right, that's what I'm calling it. That's the automorphism, given by the group element alpha H, and I apply that to n prime, and then that's HH prime. On the other hand, and then I can map this thing over here, where I would get n phi alpha H of n prime. And then I have to do the alpha to the other guys, so I get alpha of HH prime. That goes to there. On the other hand, I can map each of these guys over. This is a pair. I can map each of these guys over, and I get n alpha H, n prime, alpha H prime. And to multiply these guys together, I need to slide the n prime past the alpha H, and then I have to do that, I do the phi alpha H to it, so I get exactly this thing, n times phi alpha H of n prime, and then I multiply these guys together, I get that. So this is actually the product in the phi group. Okay, so that's one straightforward thing that you can do. As an example of an application of this, let's pretend that we're looking at, let's imagine that we're looking at a semidirect product. How about Z mod let's see, what do I want I'll do z mod 3z semidirect product with some phi z mod 2z cross z mod 2z. And let's take a look at this for example. Okay? So if I want to say what are the different kind of phis that I could get, well, so this phi, I'm trying to just understand what the semidirect products are. The phi is going to be a map from z mod 2z cross z mod 2z to the automorphisms of z mod 3z, which is the units mod 3, which happens to be z mod 2z. And okay, so we see that there's a couple of possibilities here. It's possible on the one hand that this could be the trivial map sending everything to the identity. That's possibility number one. In that case, this semidirect product would actually just be a product. On the other hand, I could have a non-trivial map, which will always have the structure of, so this will be the non-trivial map will have to be surjective. Therefore, it will have to have a non-trivial kernel. This is a group of order 4. The kernel will be a group of order 2. So I'll have to choose a subgroup of order 2 to mod out by, and then an identification of z mod 2 with z mod 2. There's only one such identification, taking the non-trivial to non-trivial. So such a phi is exactly determined by what subgroup I'm modding out by. Okay? Phi, so non-trivial phi is determined by its kernel, which is free to be an arbitrary cyclic subgroup of this, just some non-trivial order 2 cyclic subgroup. Well, there are 3 such subgroups, but any one of them can be moved to another one via an automorphism of this group z mod 2z cross z mod 2z. What that tells me is that even though there are 3 different non-trivial phis that I could write down, because of this identification, I could pre-compose with an automorphism to line any of them up. So that tells me that there is exactly one non-trivial semidirect product. So by non-trivial, I mean with a non-trivial phi, which is to say it's non-abelian. I can't just slide the h and the n stuff past each other. And of course, there's one trivial one, which is the one that's actually a product. Okay? All right, and we'll now take a look at the other way of modifying our semidirect product. In order to describe the next kind of move that we can do to change our semidirect products, let me take a little sidestep and just for our own kind of mental comfort, think about what it means to make an abstract change of basis of an automorphism. So in fact, let's consider just a homomorphism from a group to itself. Okay? Now, I mean, I'm just thinking about this in analogy with vector spaces. If you wanted to kind of think about this as some sort of like an abstract matrix or something like that, then we would kind of pick a basis and see what our, what our map does to our basis. So we might imagine, for example, let's say G is generated by x1 through xn, some group elements. And then, of course, F is going to be determined by where it takes each of these xi's. I don't know, maybe they go to some yi's or something like that. Okay? So, of course, not every choice is going to be legitimate. These are not kind of independent elements in some sense. But at least, if we know where F sends the x's, sending them to some y's will will completely determine the map F. Now, if alpha goes from G to G as an automorphism, then we can use alpha to get a new set of generators, namely alpha of x1, alpha of x2, etc. and these are going to be a perfectly valid generating set as well. And if we just decide that that alpha, if we're going to define a new group homomorphism, which takes alpha of xi, one of these new generators, to, well, the target alpha of yi, what we can think of this as is kind of using alpha as a change of basis matrix in some sense. And G is really somehow F written in a new, kind of in a new basis. I mean, these aren't really bases, these aren't really vector spaces, I'm just making an analogy. Concretely, what is G? So concretely, G, okay, I have a 50-50 chance of getting this right, I'll just go for it. Is it alpha F alpha inverse? Yeah, I think it is. Because if you take this and you stick in one of the alpha xi's, you do alpha inverse to it, that just gives you the xi back, you do F, that gives you the yi, and then you do alpha, that gives you that guy, right? So you can check that these are equal because they do the same thing on a basis. And this is the usual kind of change of basis formula that you see in linear algebra. So let me just kind of summarize this a little bit abstractly, but this is the kind of principal motivation. So if we're given some homomorphism and alpha in automorphism of G, then we get a new automorphism, alpha F alpha inverse, from, well, the new homomorphism, I guess. Alpha F alpha inverse from G to G, which we think of as the change of basis. And what we'll see is that this is another operation that we can do to change from one semidirect product presentation to another. So now, suppose I have a semidirect product in semidirect H with respect to some phi, so phi is a map from H to odd n. Then, thinking about each particular target of this phi map, some phi H is some automorphism of n. If I'm given a fixed automorphism of n, I can use this to kind of change the basis, if you will, of each of the phi h's. That is, concretely, we think of this as just conjugating phi h by the beta. So I can take this to beta phi h beta inverse, and all these taken together really correspond to a map of aught n to itself, where I take an automorphism and I compose with the inner automorphism beta. So this is inner beta. This is the map that takes some f to beta f beta inverse, and that's a map from aught n to itself. Okay, and let's see. So doing this composition, we get a new map from H to aught n. And that new map we perhaps can poetically refer to as beta phi beta inverse. So we're kind of modifying our original phi by kind of conjugating it, if you will, by a beta. By which we really mean just the map that takes H to beta phi h beta inverse. So that's how this symbol is to be interpreted. All right, if you do this, let me go ahead and erase that. Very limited board space here. If we do that, then it turns out that we get an isomorphism between these two semidirect products. And very concretely, this automorphism is described in the following way. So I'm getting a little tired, so I'm writing these things as the internal semidirect product, which is to say I'm using this notation in times h instead of in comma h. I'm just regarding these as subgroups for a moment. In h maps to, well, I'm going to do beta then h. Okay, and there's, you know, you can check that this is an isomorphism of groups. Let me just pick a particular educational detail to notice. So why is this working? Well, the defining property of the semidirect product is that if you write these things in the wrong order, then you can straighten them back out by applying the automorphism corresponding to H to N, and then you can move the H onto the other side. And if you look at where this map wants to send these different elements, it wants to send this thing to H beta of N, and it wants to send this thing to beta of phi H of N H. And for this to be a actual legitimate isomorphism, we really want these two things to be the same. Well, now these here are sitting in the wrong order. You know, the H is on the left and so the right, so we can use this rule to straighten them out, to reverse the order. And so what does that say? It says that you need to apply this thing on H to that thing. So that is beta phi H beta inverse. I need to apply that to beta of N, and then I have an H. And you can see that these are the same thing. And in a nutshell, that's why this is a homomorphism. All right. So I mean, I'll leave the actual details, you know, for you to check. But from this basic idea, this is basically why this natural map gives you an isomorphism of these two guys. So this is a particularly useful thing. It lets us use a little bit of linear algebra occasionally to tell these semidirect products apart, or say which ones are the same. So, for example, if you have something like, you know, which should be my normal subgroup. Let's see, I'll make it like, yeah, this good old example, z mod 5z squared, so z mod 5z cross z mod 5z, semidirect z mod 2z. Such a semidirect product, you know, so what is the possible phi? Such a semidirect product is given by some phi that goes from z mod 2z to the automorphisms of z mod 5z squared. And that's GL2 of z mod 5z. And so such a semidirect product is really given by specifying a matrix whose square is the identity. But what this previous argument tells you is that I can actually change basis of my vector space and say that any two matrices that are related by a change of basis actually give me the same semidirect product. So what that means is that I don't need to consider kind of you know, arbitrary matrices, but I can put them in canonical form by changing their basis. In particular, you can apply the theory of Jordan canonical forms, which we'll discuss later, to reduce the number of possibilities from like every possible order 2 matrix, of which there are plenty, to just a short list of these nice matrices. These are the possible Jordan matrices, like that. So you can reduce from a larger list to just these 5 matrices to consider. Because, you know, what we'll see is that up to conjugacy, a matrix whose order is 2 is one of these 5. And so things like that let you kind of greatly reduce the complexity of enumerating these semidirect products.